today we are going to talk about the uses of definite integral. How can you use it to do something effective for you? For example, finding areas or volumes of slightly interesting figures like circles or spheres or cones. So, that is exactly we are going to do today, finding the area of a circle, finding the area volume of a sphere and finding the volume of a cone of a given height. Now, I just want to tell you that the idea of a definite integral, what we do today, or idea of integration, that integration by taking the integral of a function from a given 2 points A to B, I can actually essentially compute the area of underlying the curve and the x axis. This idea was actually known to Archimedes, one of the greatest scientists of antiquity. So, what he did was that he took the circle So, I am taking this circle, what I want to find its area. So, what I am taking some points say A, B, C, D, E, F, and this is a center O. What I do is I join to the center O all these points. Is like cutting up a cake, and then you join the adjacent points. Adjacent means from F I can go to A, but F I can directly can't go to C. If I walk over the arc or walk over the circumference, if I move from F and go towards C, either I go through A and B or I go to E and D. I cannot. So, E, F and C are not adjacent, or F and B are not adjacent, while F and A are. So, what I do is now calculate the area of these triangles and then basically calculate the area of this polygon. So, we have now covered a good amount of area of the circle with these little parts left out parts. So, the brilliant idea which Archimedes thought about was, okay, I take the area of the circle, the area of this polygon and store it. Now, on the same circle, now I increase I here had 6 points, now maybe I will make some 12, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, I have 12 points, and now I am trying to do the same operation. Let us see what happens. And then so, what I have done, I have made the side of these polygons, the length of this side smaller and smaller. So, now if I take this new polygon and compute the area of the polygon, I have left out much lesser area than I had left out earlier. So, you keep on increasing the number of points of the circumference, which is called partitioning the circumference with points, and then you try to find the areas of the hexagon. As you move, the areas go and increase and increase and increase and gradually go towards the area of the circle. So, Archimedes somehow had introduced the limiting process plus the idea of integration. For example, how do I now, we are now talking about one thing, how do I use calculus to find the area of a circle? And I will go back and use the very interesting book of Larry Connick, the cartoon one of course, and tell you how to do the stuff. So, you take a circle, say of radius r, does not matter. So, you have taken a circle of radius r, now once you have taken a circle of radius r, this is 0, this is r minus r. What I can do is I can take small circles of radius ri, say circle number 1, circle number 2. So, I am basically dividing up the original circle into pieces of thin circles, each having a radius which is delta r amount, a fixed amount more than the radius of the inner circle. So, if I have r 1, if I start with this smaller circle inside, the smallest one, if it is r 1, then the next one has a radius r 2 equal to r 1 plus delta r. So, similarly, I can have the circle with radius r I and radius r I plus delta r, this particular dotted region. So, basically it is consisting, this whole circle is consisting of some strips like that. If I can find the area of those strips and add it up, then I can essentially get the area of the circle. So, if let us see what is the area of this spot. That is interesting. Okay. So, what I do is I essentially I will take my delta r to be pretty small. So, the thins are so stripped. So, there is hardly a difference between r I and delta r I. When r I and say, so r I, so r I plus 1 is r I plus delta r I. So, this difference between r I plus 1 and r I is really small. So, what I can do is I can cut this particular strip here, and once I cut it, I can then now open it up like this. So, these are the thing radius r, but the length of this side, one of the sides, be very clear. The length of one side, I have cut it up, it is a very thin rectangle, is nothing but the circumference of a circle of radius r I. So, area of this is 2 pi r I into delta r I. Now, what I need to do, so what I need to do is, now I have the area of this particular strip, now I have to sum it up. So, I have to really sum this up from I equal to 1 to whatever slices you have made. I did not really count the slice, but I have to take the limit of this as delta r I goes to 0. When delta r I becomes very small, so delta r I actually is representing the differential of r I's. Essentially, finally, the differential of the radius r, we can just, instead of telling r I, we can just take r and r plus dr. So, this limit is nothing but the integral. So, it is you have taken the sums of the areas. So, you get an area, but what are you trying to do is you get an area, you take the individual strips and you get an area, but what you are trying to do is, you know that here this area that you have computed, there is a slight discrepancy, because one side it is the radius value is, the length of the circumference is 2 pi r I, and the other side it is 2 pi r plus dr. So, you have to take into account of this difference, and this actually, which means that you have not completely got the area of the circle, and so as you, so there is a overestimation or underestimation. So, as you make delta r I smaller, that is dri, this delta r I is very small. So, this as you make r I approach r I plus 1, then you actually get what you are doing, then this idea is correct. So, then that is exactly equal to the integral from 0 to r, and then this is nothing but r square by 2, right, pi r square 0 to r, and this is pi r square. So, how do you find the volume now of a sphere? Now, we have to understand one very important thing. A sphere, I will just show you, is something like this. So, how do I look at a sphere? I basically want to cut the sphere into small, here I cannot take slices like this. So, basically I can cut this, it is like a fruit, and I can cut it, slice it up into very thin pieces, and basically then add the so called volume of those thin pieces and add them up. But if you take a very small thin strip and cut it out, then you will realize that it is not really a part of the volume of that element is not really a cylinder, though it looks like a cylinder, it is not, because it looks as if it is a part of a truncated cone. So, because there is a difference between the radius of one side of the strip and the other side of the strip, but we can imagine them that the difference is so small that we can imagine them as cylinders. So, because we are imagining them as cylinders, we cannot say that when we add up those cylinders, the volume of the cylinders, we get exactly the volume of the sphere. So, what happens is that we have to go to the limiting process of telling that the difference between the two radiuses, because when you take a strip, as we will just see, there will be small difference, that difference goes to 0, and then you will actually reach the actual area. So, this is the very basic limiting idea of Archimedes, which we are still using now. You see, what happens is, what we are doing is the following. Basically, here is a sphere in 3 dimensions of radius r. I want to find its volume. So, what I have done is that I am looking at one section of the sphere, and what I am doing is that I am looking at a very thin strip cut out from it. I am looking at the volume of this strip. So, this is your xi, which corresponds to the first strip. So, you have the radius, say Ri, and then Ri plus delta Ri. This part, if you go from the center of the sphere, has radius Ri, and the remaining part has a distance of Ri plus delta Ri. Now, what do I have to really do? So, this is the most critical thing. So, this is your xi. So, I really need to find so this looks like a thin cylinder, though really it is not a cylinder. If you really slice up the sphere, it is not a cylinder, it is a truncated cone. There is slight slanting on the two sides. These sides are slanted, you see, you cannot say it is a cylinder, but because we are assuming delta r to be small, we assume that it is a cylinder. Basically, we are thinking that we are putting up some cylinders and it should look like a sphere. It will not, only in the limiting case it would, and that is the whole idea of the limiting case, the charm actually. So, basically you have the radius r, and then you have this xi here, sorry, this xi is here, the horizontal length. Now, what should be the vertical length, which I will find by the Pythagoras theorem, and that will give me the radius of this infinitesimal cylinder or elemental cylinder. So, this is nothing but root over r square minus xi square. Okay. So, now what is the area of this circle? The area of this circle is actually root over r square minus xi square whole square into pi, and the volume of the cylinder is nothing but this little distance, which is actually delta Ri. Basically then we are having pi of r square minus xi square delta Ri. So, the area, so what you do, so if you sum up all the cylinders, so basically xi is some point which is essentially lying in between these two ends of the cylinder or the elemental cylinder. So, it will r minus xi square delta Ri. So, I is whatever number of cylinders you have pieced up the sphere into. Now, once you take the limit of this, so the volume of this elemental cylinder is this, once you take the limit of this as delta Ri goes to 0, that will give you the volume. And what is this? If you write, this is nothing but 0 to r pi r square minus x square into, so I will, instead of writing del Ri, I should write here del xi, because here I am looking at the change, here it was xi, here it was xi plus del xi. So, the actual change in the radius, whatever I am writing as Ri here is actually not really Ri. So, this part, so it is xi, if this is my xi at this end, and then this part at this end. So, this coordinate is, so this coordinate is xi plus delta xi, and this coordinate is xi. So, I am taking as if the xi thing, that this part. So, I am taking this xi thing and I am calculating the area of the cylinder. Of course, there is another way of taking an xi between this slab, that also does not matter, and then you can take this to be some delta xi, this length to be some delta xi, you can call this delta xi, does not matter, you can take any x. So, anyway, so this I should not write delta Ri, the symbol should be same, then I should write Ri here instead of xi. So, this is delta xi. Please please check it up there. It is just, I confuse usually with symbols. So, here, so this is this, and this will give you, which you can compute out easily. Now, this is very interesting. Suppose you are asked to compute an integral of the form 0 to a root over a square minus x square dx. How will you do it? Because if you are doing it, if you look at this, what does this equation tells me? If this is the function, then it is, so this will give you y square plus x square is equal to a square. So, this function represents the upper part of the circle from minus a to plus a, and area of this is pi a square by 2, and we are looking at half of that because of the symmetry. So, this is nothing but pi a square by 4, the answer is pi a square by 4. So, if you know the areas, you can actually compute out integrals like this. So, I will leave you as an exercise that without really integrating, find the area enclosed in the ellipse do not compute the integral by hand. So, another important problem which I really want to talk about is if you take a cone, an ice cream cone which all of you eat, and so take an ice cream cone, and basically a cone is a 3-dimensional object. So, take this x axis, this is a y axis, and this is a z axis. So, you take some sort of a line y is equal to a x or z equal to a x. So, you take this line z equal to a x, right. This is the z equal to, sorry, maybe a y I should say. So, let me put this as y and this as x. And then you rotate this line along the z axis, keeping a fixed angle say theta. And what you generate finally is called cone. These are called solids of revolution, because you are revolving some lower dimensional object and getting a higher dimensional object. So, this is a cone. The question is, how do you compute its volume? The answer is, if this is my height, so I give a fixed height to the cone, this is my height h, the answer is 1/3 pi h cube by a square. Now, can you find this by calculus? Use definite integrals. There are many things about definite integrals we have not spoken about, but this time is very short. It is essentially a tremendous crash course. So, again you cut it into cylinders and then take the limiting process. You know that this is really not a cylinder, it is slightly like a slanted thing, it is like a partially part of the cone, it is not really a cylinder. So, it is a truncated cone sort of thing. So, but then you really need to figure out what is the radius here, what is the radius here, find the area of the circle and then take multiply by this distance which is del z basically. So, you take zi and zi plus del zi, and then so del zi into what should be the, so if you look at this radius is nothing but this distance xi. This radius is the distance xi at the height xi. So, zi here by, so xi the radius is obviously coming from this equation xi equal to zi by ai, and once you know that what is the area. So, area is pi into zi by ai whole square for this elemental circle, this elemental circle, you know the area is pi times zi by ai whole square, and that you really you know that you have to multiply with del y. So, it is essentially this, and that you have to integrate from 0 to h, and that will immediately take you to this answer. It is not dy, sorry, dz, because this delta zi, this distance is delta zi, this distance what I am now marking by pen, this distance is delta zi, so dz, and that will exactly take you to this, and that ends our discussion about definite integrals. Thank you very much.